Hello and welcome to this video. In this video we're going to continue on with the circular motion topic. In the first video back at when we looked at the introduction, we said that we can translate all of these linear properties of motion into a circular property of motion. We started off in the first video by translating from linear velocity to angular velocity, and in this video we're going to translate from linear force to centripetal force, and from linear acceleration to centripetal acceleration. Okay, so let's first start off with the acceleration. Okay, now what we know from what we said briefly in the first video is if I draw a circle, I could probably do better than that. If we draw a circle like this, it will have some radius, and let's just assume for the case of this that I have a ball that's just got a string attached to it, and there's a person at the middle that's just going to swing this in a circle. Now we know that the acceleration linearly, acceleration is the change in velocity divided by the change in time. Now in the case of centripetal acceleration, this is going to be the case, except centripetally, so circularly. So centripetal is just the fancy word for saying circularly, but since circularly is a really hard word to say, we just say centripetal because it's much better. The acceleration is the change in the angular frequency divided by the change in time. So this is very similar to what we did before. So what we're going to say is we have some velocity here, and the way that we know acceleration is happening is that if I were to continue spinning this around, so even if the velocity is the same, and I'm going to put here these lines here because this means the magnitude of the velocity. So even if the speed that this is traveling at all the time is the same at all times, the direction of v is changing. Okay, and since the direction of v is changing, that means that we're going to end up, when it's going completely down on this side, if we had a case where it's completely down and we go here where it's completely vertical, let's just define the vertical to be positive. We're going to constantly switch between positive and negative velocities, which means if we have a constant change in velocity here, it's going to lead to a constant change in acceleration. Therefore, or it's going to lead to a constant acceleration. Therefore, acceleration must be happening, must occur. Okay, so it doesn't matter if the velocity of the thing increases or not, because you're changing direction, you have a change in both the linear velocity and the centripetal velocity, and so you're going to end up, or the angular velocity, and therefore you're going to end up with some acceleration. Now we can obviously put an equation on this acceleration, and in your formula sheet you will find that the centripetal acceleration can be written as v squared over r, and it can also be written as omega squared times r. Now the reason that these are both correct is since the acceleration needs to be measured in meters per second squared, the velocity, we start with meters per second, we're squaring that, we're going to divide it by meters because this is just the distance. We end up with meters squared, seconds to the minus 2, divided by meters, cancels out one of those, we end up with meters per second squared. So this is a valid equation, and omega squared r works since omega is just v over r, so omega squared is therefore v squared over r squared, so I need to times this by r, so I basically cancel out one of those, and then I end up with the same expression, therefore I must have a centripetal acceleration. And like all accelerations, the centripetal acceleration is a vector. Centripetal acceleration is a vector quantity. Okay, and now in this case, a good question to ask would be, well, what direction does that point in? Surely it will constantly change. There's no way you can have a constant acceleration in this case. But what we actually find is that if we refer back to laws, like we said in the first video, any law that we know in a linear motion must also be true for circular motion. We just have to change a few things. And one of the biggest laws that we know is Newton's second law. So we know F is equal to ma. And this means that the force is in the same direction as the acceleration. So our only question now has to be, what direction is the force in? So for this, I'm going to scroll down and we're going to now look at centripetal force. Now, some of you might have already, or most of you would have already met centripetal force at GCSE. So you have a rough idea of what it is, but we're now going to add some equations to it. So we'll have the same example set up. So I have a ball on a string, and this is going to be swung around in this direction. Now, physically speaking, if we have a ball on a string and we're constantly spinning it around, the only proper force that we have present is the tension in the string. And the tension in the string is going to point towards the center of the circle. Okay, so the centripetal force, by definition, always points towards the center of the circle, or of the circular path, because you can have parts where you have a partial circular path. It always has to point towards the center of the circular path. It doesn't matter what position it's in. If the ball was here, the rope is here, so the tension is still pointing towards the center. Now, another key thing here is, why are we calling this the centripetal force when it's actually just the tension in the rope? And actually, the reason we have to do that is because centripetal force is a resultant force. Okay, this is the resultant force which occurs when objects move in circular paths. Okay, so it's the summation of all the forces that are acting on this object that contribute to the centripetal force. And we find that a fundamental thing for anything moving in a circle, the force has to always go towards the center of the circle. You can take my word for it by doing this, by just looking at this diagram, and it's kind of clear that surely if it's going to continue moving in a circle, the force has to always point towards the center. If you don't really believe me, then go grab a football. If you take a football and try and just dribble it in a circle, you'll find that when you kick the ball, you will always kick it towards the center of the circle to try and keep it moving in a circle. So you'll always kick it towards the same point on the floor. And that's a good way of just visually basically assuring yourself that this is true. Okay, or you can just take my word for it. So the centripetal force is always pointing towards the center of the circle, and it's a resultant force, which means it's made up of other things. In this case, it's tension. If we were to consider a car going on around a roundabout, it's the friction on the road that's keeping it going towards the center. So actually the friction is transverse to the direction that you're moving in on a roundabout, because you have a partial angle when you're moving. So the friction keeps it in the center. If you're on like a roller coaster and you go over a hump, you end up with gravity being the centripetal force, and so on. Okay, we'll do a video where we look at some more real life applications of centripetal acceleration and centripetal force. But for now, we understand the basic concept. We have to add an equation to this. Now, like we just said, if these laws have to work in both linear and circular motion, we've just defined that A is actually equal to v squared over r, or it's equal to omega squared r. Therefore, the centripetal force that we're measuring, so this means therefore the force must be m times v squared over r, because I'm just doing m times my acceleration. So my first case is I put an m here, or m times omega squared r. So these are my two formulas that I can use to define centripetal force. Again, it is a force, so it is traveling in the same direction. And since we now realize that the force is always traveling towards the center, it means the acceleration is also always traveling towards the center. The object will both be pushed and accelerated towards the center of the circle whenever it moves in a circular path. Thank you for watching.